My name's John Adams, and I'd like to introduce you to the world of Spektrum technology. Back in October of '05, Horizon, under the Spektrum brand, introduced the first ever spread spectrum radio for model aircraft. The radio is called the DX6, and it offers many advantages that were previously unavailable in conventional 72 megahertz systems. Those advantages include you no longer have to wait to go fly. You no longer have to wait for a frequency. You no longer have to worry about getting shot down by somebody inadvertently turning on your frequency, or vice versa, by you mistakenly turning on. There's no way you can shoot anybody else down. This system is completely immune to environmental and model-generated interference. Also, you no longer have to worry about frequency control. If you go to an event, like we were at a recent event in Columbus, Ohio, a large indoor flying event where several hundred people were there, or if you go to your local flying field where there are 15 or 20 folks, you no longer have to worry about interference issues. You no longer have to worry about what frequency you're on or what frequency they're on. With the DX6, when you're ready to fly, you simply turn on. I'd like to take the next few minutes to explain to you some of the technological advantages of spread spectrum technology. But first, it's important that we understand what our current technology is all about. Currently, we're operating our aircraft on 72 megahertz narrowband systems. And anybody that has ever flown on a narrowband 72 megahertz system knows some of the pitfalls. Number one, we're on a single channel. Number two, that's a very narrowband channel. And we have to be extremely careful, and we are extremely vulnerable to many causes of interference. One of the main obvious causes of interference is somebody else being on the same channel. This includes other modelers that may be at the flying field, but in addition, the FCC allows high power 72 megahertz users that are actually in between our channels. So for example, here we're in Champaign at our local club. We have several local businesses that transmit on 72 megahertz on very high output power, as much as 50,000 kilohertz. They communicate with some of their drivers out on the field. And in fact, at our field here in Champaign, we have 5 frequencies that are no longer safe to use and to fly on. So also, other issues that we have on 72 megahertz, we're extremely vulnerable to model-generated RF noise. In fact, here in our Horizon Service Center, we service thousands of radios a year. And actually, in the studies that we do, we find that the majority, in fact the vast majority, of the radio interference issues that our customers are having are actually not environmental issues or defective radio issues. They're actually caused by RF noise or by interference actually generated by the model itself. This includes noisy motors, noisy speed controllers. It includes metal-to-metal noise. You know, if you have pull-pull cables in the back of your airplane and it rubs through the insulation and those two metal wires touch, that causes radio interference. Or it can be a bad bearing. Or in helicopters especially, you have an aluminum or carbon-framed helicopter and a bolt comes loose and those two conductive parts vibrate together. Well, that causes model-generated radio interference. And that is one of the biggest causes of issues on our 72 megahertz systems. As the example here on the T-Rex, you'll notice that the receiver is actually mounted directly on top of the speed controller. With a conventional 72 megahertz system, you'd never do this. You know, the speed controller obviously is causing RF noise, and the motor wires, of course, are going right back around the back side, and here's the receiver. On 72 megahertz, you'd never be able to get away with this. With spread spectrum systems, I actually have 3 T-Rexes that are set up identically to this, and all the receivers are mounted directly to the speed controller, and I've never had a glitch. And these helicopters, between the 3, they probably have close to 300 flights on them during testing. Never had a single glitch. You'd never get away with this on 72 megahertz. It's just common practice with spread spectrum. With spread spectrum, all that, including model-generated issues. And by the way, I didn't mention there's also 3IM and 2IM issues. That's issues where 2 or 3 or multiple users on 72 megahertz turn on frequencies and they create a harmonic, which then causes an interference on a 3rd frequency. So as I said, those of you that fly typically 72 megahertz, you know what I'm talking about. Spread spectrum totally eliminates all those issues. In fact, spread spectrum has been in use for several years by government agencies like NASA, like the CIA, like the military, for mission-critical applications. Typically, guided missiles, where you're guiding nuclear warheads across enemy territory. I mean, you can imagine how mission critical that is. NASA uses this to communicate with satellites and even to control their spacecraft. So spread spectrum is a technology that's been used for several years by government agencies, by the military, and because it is absolutely provides a secure, bulletproof RF link. Spectrum's DS6 actually transmits on the 2.4 gigahertz band. The 2.4 gigahertz band is called the ISM band, which stands for Industry, Science, and Medical. And obviously it's regulated by the FCC. The FCC, when they developed the 2.4 gigahertz band, set aside some very specific rules that make this ideal for model airplane applications. Those rules include, number one, anything on this band is limited to a maximum of 1 watt of output power. So consequently, you can't have these huge 50,000 kilohertz transmitting stations on the 2.4 gigahertz band. Because according to the FCC, you're limited to 1 watt. What this does is this prevents long-range interference from commercial users or from any device. So potentially, the only things that can interfere with you have to be within about a 3-mile radius of your transmitting station. So imagine if we were on 72 megahertz and had the same type of regulation, the only thing that could interfere with you, would be within 3 miles away. Boy, that would sure clear up an awful lot of things on our 72 megahertz band. And of course, it certainly makes it much better for our model aircraft use for the 2.4 gigahertz band. In addition, the FCC mandates a function called collision avoidance. Collision avoidance states that any system that turns on the 2.4 gigahertz band must be cognizant or aware of other things that are on the band. In the case of our system, when you turn the transmitter on, the first thing the transmitter does is scans the 80 channel 2.4 gigahertz band, looks for an open channel, and when that open channel is found, then it turns on and transmits. And in our case, which we'll explain in a few minutes, this actually has 2 receivers and has 2 transmission frequencies in one. This system actually scans the band a second time, looks for a second open frequency, and turns on that frequency. So the collision avoidance absolutely prevents the system from coming on a frequency that's already taken, and in addition, it prevents other systems of any kind. This includes Wi-Fi systems, this includes wireless routers, cordless phones. All those, anything that's operating on the 2.4 ISM band must have collision avoidance. I'd like to take the next few minutes to describe to you how Spektrum technology works with the DX6. One of the first things you'll notice when you take a look at the receiver is that the receiver actually has 2 antennas. That's because the receiver is actually 2 antennas built into one. We call this dual link technology, and we've applied for a patent. This is one of the big technological advances that we came across that allow the system to be able to be used in aircraft. We're actually transmitting on 2 frequencies and receiving on 2 frequencies simultaneously. Let me tell you a little bit more about how the system works. The 2.4 gigahertz band actually is broken into 80 channels. So each channel has 1 megahertz spacing. That's huge. With our 72 megahertz, we're actually 20 kilohertz spacing. So we actually have a 1 megahertz spacing with 2.4 gigahertz spread spectrum. Each transmitter and the electronics in each transmitter has a chip that has its own GUID, or globally unique identifier. Think of GUID as a secret code. That code, by the way, has so many digits that there's the potential to have over 4.2 billion possible combinations. So the transmitter comes from the factory with its GUID, or globally unique identifier, already coded in. In order for the receiver to recognize the transmitter, you have to teach the receiver the GUID, or globally unique identifier. We do that in a process called binding. Binding is a process which involves a bind connector and the receiver. And in order to do the bind function, it's necessary to plug the bind connector into the bind battery port, and then you turn the system on. When you do that, you'll notice that there's an LED, an orange LED, which blinks continuously, indicating that you're in the bind mode or ready to bind mode. On the transmitter, on the back of the transmitter, you notice that there's a button. That's called the bind button, and it's also used to do a range check. In order to bind the transmitter to the receiver, you need to push and hold the bind button while turning the system on. You'll notice that the LED flashes for about 5 seconds, and then the transmitter connects to the receiver. The receiver will then, the orange LED will then go solid on the receiver, and you'll have control. That's what binding is all about. And from that point on, this receiver is bound to this transmitter and will only take commands from this transmitter alone and nothing else. In fact, there's nothing else in the world that can cause control or take control of this receiver except for this transmitter. By the way, you can bind as many receivers as you choose. If I had 50 receivers here, I could bind them all to the same transmitter, and I can also rebind this receiver as many times as I choose. I can rebind it to another transmitter, or as we'll find out in a second, during that binding process, we also are setting the fail-safe positions. Once the system is bound, you're ready to go. And by the way, the system is pre-bound from the factory. It's pre-bound with a low throttle fail-safe, which we'll talk about fail-safe setting here in just a second. But what I'd like to describe to you now is how the system actually works. So with a receiver that's been bound to a specific transmitter, when I turn the transmitter on, the transmitter scans the 80-channel 2.4 gigahertz band, looking for an open frequency. When it finds an open frequency, it turns on and transmits on that frequency, thus occupying that frequency. Then the transmitter scans again. It scans looking for an open frequency and locks on that open frequency, and now it's occupying simultaneously 2 frequencies. When I turn the receiver on, the receiver scans the 2.4 gigahertz band looking for the GUID from the transmitter. When it finds that GUID, it recognizes the frequency that it's on, and it locks on that frequency, and at that point the receiver is connected to the transmitter. This whole process typically takes about 3 to 8 seconds, so it's very quick, very rapid. By the way, if I turn the receiver on first, the receiver is scanning the 2.4 gigahertz band, but since the transmitter's not on, it can't find its GUID, and it will scan indefinitely. At that point, at some point, if I turn the transmitter on, then the GUID becomes available on the 2.4 gigahertz band, then the receiver will lock to the transmitter. So that's how the system connects. The DX6 incorporates a smart fail-safe system that's very unique. We set the smart safe system during binding, and that's the servo positions during binding. So during the binding process, as we mentioned just a second ago, when you push the button, it's necessary to first position the sticks, normally low throttle and neutral stick position, in order to establish your preset fail-safe positions. Now, during the binding process, whatever stick positions that you have, and that includes trim positions, sub-trim positions, gear switch positions, whatever positions you have, that becomes the preset fail-safe. The really unique thing about smart fail-safe is it works very differently than most conventional fail-safes that were typically on PCM systems. That is, if I first turn the receiver on and no signal is present. So if I go over and turn on my model, and I don't turn on my transmitter, first off, you normally wouldn't do that with an FM or PCM system. With our system, you can certainly do that. If you do that, what happens is all channels except for throttle go to their preset fail-safe positions, even though the transmitter has never been turned on. So the elevator, rudder, aileron, gear switch, flaps, and so on go to their preset positions. The throttle, however, goes to a position where there's no signal being generated. This is important because if no signal is generated to an electronic speed controller, then the speed controller can't come on. When I turn the transmitter on, then make a connection, then all the servos go to the desired position. You know, if I have this stick at low stick or high stick or wherever, that's where the ailerons, everything acquires the positions where the stick's at. When I turn the transmitter off, all of the channels except for throttle hold last position, and the throttle goes to the preset fail-safe position, which is low throttle. The reason that we do this is from a safety perspective. And in fact, let me give you a demonstration on how Smart Failsafe works in practice. Okay, I have an electric E-flite yak here. The failsafe has already been preset. The failsafe has been preset to low throttle, and also to the ailerons are set to neutral, rudder set to neutral, and elevator set to neutral. So typically, you normally wouldn't do this, but I'm going to displace all the surfaces. And of course the motor's plugged in. And what I'm going to do is plug in the battery pack. And you'll see that all the surfaces go to their neutral position. That's the preset fail-safe position during binding. You'll also notice that the throttle, this happens to be a Castle Creations throttle, the throttle is getting no signal. So we haven't armed the throttle. So if I turn the transmitter on in any position other than low, it's not going to start up because the throttle hasn't been armed. And when it's armed, you can tell because it'll beep at you. So I'll turn this model over, and the transmitter's still not on, but everything is in its preset fail-safe position. Now, you normally would never do this, but what I'm going to do is go to half throttle, which is something you wouldn't do, and I'm going to turn the system on. Watch what happens. It's connecting, it's transmitting on 2 frequencies, and it just connected. So as you can see, now I have control of everything, but even though I was at half throttle, the motor isn't throttling up. That's because that received no signal. When I turn the transmitter on, now it's seeing a signal that's above the arming point. When I reduce the throttle, let's listen to the speed controller. When I reduce the throttle to idle, you hear the beeps, now it's armed. And now we're ready to go. Now if for whatever reason I lose the signal, and I'm going to go to partial throttle here, and I'll lose the signal, or let's say I turn the transmitter off. That's a way to lose the signal. What you'll notice is when I turn the transmitter off, the motor goes to the preset fail-safe position, which is idle, and all other controls go to their last hold position, which in this case they all happen to be neutralized. So that's how our smart fail-safe works. Obviously, when you regain control, everything operates again like normal. And when you lose the signal, same thing. It goes back into the fail-safe hold. All controls go to their last hold position. The throttle goes to the preset low position. By the way, the fail-safe comes pre-adjusted. Everything is at neutral except for the throttle, and the throttle comes at low throttle. However, when you get your system, it's very important, and in fact we have it in the instructions in a separate sheet, it's very important that you bind the system at low throttle, just to be absolutely sure that if you do have loss of signal, that you go to low throttle and not high throttle. That's how Smart Failsafe works. The DX6 incorporates a unique range check system that allows you to range check in a very similar way that you range check typical 72 megahertz systems. With 72 megahertz systems, of course, you collapse the antenna and then you do a range check at a specific distance, wiggling the sticks, being sure that the controls work at a specific distance that you paced off. Well, with the DX6, it has a fixed, fairly short antenna. It's impossible to collapse it. So what we've done is we've incorporated, and in fact we've applied for a patent for this, incorporated a unique range check function. So you'll notice by turning the transmitter on, and you'll notice that the bind button is also a range check button. When I have the transmitter on and when I push and hold the bind button, this actually attenuates or reduces the output from the transmitter, and this allows me to do a range check. So in order to do a proper range check, after I have my model ready to go, I plug the battery in, and it would be a good idea to have a friend hold the model or to stake the model down so that it won't get away. And then I walk 30 paces, which is 90 feet away from the model. I face the model with the transmitter and the receiver on, and then I push and hold the range check button, and I wiggle the sticks. And if everything goes well, you'll have full control. If for some reason you don't have full control of the aircraft, then you should probably look to be sure that you don't have something wrong, like antenna orientation issues or something not hooked up properly in the airplane. If you continue to have troubles, then you need to get a hold of our Spektrum Service Center. But 99.999% of the time, you'll have full control at 30 paces or 90 feet, and it's time to go fly. By the way, we highly recommend doing a range check anytime you, of course, equipped a new airplane, obviously a new receiver, or make any modifications to your airplane that affect the radio system. So it's always a good idea, not only with 72 megahertz to do a range check, but also with 2.4 gigahertz. The DX6 was developed and designed specifically for park flyers. That includes a lot of the aircraft that you see here. Park flyers constitute small electric airplanes. That also means micro and mini electric helicopters. The reason that it's for park flyers only, obviously that was a great place to start for spread spectrum, because spread spectrum technology is very difficult to incorporate into aircraft. The reason that we absolutely avoid using it in 40 size or larger aircraft are twofold. One, you have some range issues. With typical airplanes of this size and helicopters of this size, you can fly these airplanes to your limit of sight and still be in full control. In fact, I've had the Yak, I've had the Ultimate, and in fact some of these little micro helicopters as far away from myself as I can possibly see. In fact, to the point where I wasn't sure I was going to get them back, not because of control, but because I simply couldn't see it. And I had absolutely total control, no dropouts, no loss of signal, no loss of control. So for these type of aircraft, we have more than adequate range. In addition, there's an issue inherently with 2.4 gigahertz in that it's a somewhat directional signal. And there's a function called antenna fading. So in fact, that's why we have 2 receivers and 2 antennas on each model. One of the things that happens with 2.4 gigahertz is when these antennas get behind something in the airframe that causes blocking, like a metal or carbon fiber or a conductive item, like for example, if this is in a turbine model that has a turbine tube running down the middle, and if these antennas are hidden behind that antenna, behind that turbine tube, you'll see a degradation in signal. Same thing with carbon fiber frames in helicopters or large gas engines. When this is actually behind it, you will see a reduction in range because of what's called antenna fading. So consequently, that's why the first system that we're offering is for park flyers and for park flyers only. And we strongly recommend that you limit the use of this to park flyers. Even though we know you're going to go out there and you're going to test these systems and you're going to say, I got 3,500 feet or I got 0.6 of a mile. Even in those cases, please limit this only to park flyer use. One of the questions that we're frequently asked is what's AMA's position on spread spectrum and spectrum technology, and specifically the DX6. It's very interesting because approximately 6 to 8 months before we released the DX6, myself and a couple other Spektrum developers actually went over to the AMA and talked with Steve Califf, and of course we asked him to be very confidential with the information that we gave him. We gave him some car Spektrum systems, because we've had the car Spektrum systems available for almost a year now, so we gave him some car specific Spektrum product that he was able to test. And we basically told he and the AMA that we're working on this stuff. We know several people are working on this kind of thing, and it's very important that they be aware. And quite frankly, from that point on, I've been in contact with Steve almost weekly. We've been keeping him abreast of what's been going on, and he has been incredibly supportive. The AMA has been incredibly supportive with Spread Spectrum. In fact, they did an article on their website on modelaircraft.org that talks about the DX6 and Spread Spectrum and how it affects their modeling community. Also, they have Spread Spectrum systems. We sent them one of the first production DX6s, and of course they've tested it, and they did a fantastic article in Model Aviation that talks about Spread Spectrum being used there at the AMA website, or at the AMA flying site in Muncie, Indiana. So it's fantastic, the support, and we appreciate the support that AMA has given us. Their position has been, and in fact you'll read this on their website and in their articles, that hey, this is a new technology, it is revolutionary, it will change the way that we fly radio control, and they're telling their members that hey, when somebody shows up at your field with a DX6 or another spread spectrum system, don't worry. This stuff is well tested. We've tested it here, and we're in the process of testing it further. Allow those people to fly at the field. You'll have absolutely no issues. In addition, the AMA is quite appreciative because this is a park flyer radio, and one of the big issues that the AMA and flying sites have been faced with lately is this explosion of small electric airplanes and helicopters. The popularity of these things have grown just unbelievable, beyond what any of us could have ever imagined. And now we have people flying these types of aircraft everywhere. You have them in parks, ball fields, even in side yards, backyards, places where they were never flown before. Unfortunately, when these systems are on 72 megahertz and they're flown near flying fields that use 72 megahertz systems, they can cause some catastrophic issues. Fortunately, there haven't been too many around the country, but just inherently, because they're flown in these areas, they can cause problems. So the AMA is extremely supportive of this as a park flyer radio because it eliminates all those types of problems. So when you get the chance, please take a look at the AMA website and the Model Aviation magazines and look for future articles and future information coming out of the AMA. And we certainly thank AMA for their support.
Can you tell me what the actual range is of the system?
The system is designed specifically for park flyers, which include small airplanes, electric airplanes, micro and mini helicopters. The system has more than enough range to be able to fly these type of aircraft at the point of sight. One of the reasons that we don't publish a specific range is conditions vary quite a bit. Things like humidity, the ground cover, and even the installation can affect range. When people press us to ask specific range, in testing, and believe me, we've done a tremendous amount of testing, we typically get, in worst case scenarios, 12 to 1,500 feet. In some instances, we get a lot more range than that. However, as I said, it varies just like your conventional system, it varies with conditions.
Can I use other brands and sizes of servos, including digitals?
We get that question quite frequently, and yes, you can use all types and sizes of conventional servos. It uses a conventional universal type connector, and you can plug in, of course the system comes with S75 micro servos, which are appropriate for these types of aircraft, but certainly any brand including JR, Futaba, Hitech, or any of the off-brand servos as well as digital. You can even use giant scale servos if you choose. So all conventional servos are compatible with this system.
Why park flyers only, and what would happen if I installed it in, say, like a 40 size trainer?
In some instances, we have about 1,400 feet of range. Now, normally, that's enough range for most 40 size trainers and so on. Obviously, not enough range for giant scale aircraft or jets and so on. However, there's an important thing to understand. There's a function which is called antenna fading. So, in fact, that's why we have the dual link system. We have two antennas. However, 2.4 gigahertz is somewhat directional, and it's possible on some more sophisticated aircraft that the antennas will be blocked by some of the internal components found, for example, like in a turbine aircraft or in an aircraft that has a lot of carbon fiber or has a big engine. Those things actually can block or hinder the signal getting through. So conventional park flyers, as we have here, are simply made of foam, and they don't have a lot of those blocking type of devices. So there are two reasons that this is intended for park flyers only, or designed for park flyers only, or limited to park flyers only. One is range, and then secondly is the issue that we talked about, the fading. So if these antennas were blocked by a turbine pipe, going down the center of an engine, that would cause reduced range. And yes, we are working on systems in the future which will allow those other type 40 size and larger type aircraft to be used.
What else is on the 2.4 gigahertz, and how does that affect Spektrum?
So the 2.4 gigahertz band, as we mentioned in the seminar, 2.4 gigahertz band is called the ISM band, which is the Industrial, Science, and Medical band. And typically, some of the other users include Wi-Fi systems, which are wireless internet systems. It also includes some cordless telephones. It also includes some wireless servers. And in addition, there are some medical things which are on it. The important thing to remember is the FCC limits 2.4 gigahertz on any of the devices to 1 watt. So the only potential interfering sources have to be 2 miles or less from you. So that greatly reduces the amount of interfering items, which, for example, if somebody has a wireless internet, but they're 5 miles away at the corner cafe, there's no possible way that they can interfere with your system because of the regulations of the FCC with low 1 watt output.
How much current does the receiver use?
The receiver uses 40 milliamps. Now, of course, there are two receivers, as we talked about in here. A conventional receiver, like we use now, typically draws about 10 milliamps, while this uses 40 milliamps. So it's minimally more current than a conventional receiver. You typically wouldn't expect, your flight time is going to be very similar to a conventional airplane. The additional 30 milliamps are used to operate the second receiver and the electronics in here, and it's really as of no consequence.
How do I know what channel I'm on, and do I need to know what channel I'm on?
That's a good question, and the way I would respond to that is if your cell phone rang right now, what channel are you on when you pick it up? It's exactly the same type of technology. When you turn the system on, the system scans the band and selects first an open channel out of the 80 channels, and then it acquires that channel and then selects the second channel. You don't need to know, there's no need to know, just like with a cell phone, just like when you do this with your cordless phone at home. If for some reason you absolutely need to know, there are devices which are called Spektrum analyzers which can show you, but the collision avoidance, which the FCC has incorporated into the regulations, absolutely prevents individuals from causing interference. And then you have the backup issue of the GWID that we talked about. So there's no need to know, but believe me, an awful lot of people find that frustrating. When they turn on, they want to know what frequency they're on, and it's just something you have to get used to.
If I show up at an event or the flying field with a Spektrum system, what do I tell the other pilots or the organizers?
Yeah, that's a great question. The AMA actually did a really fantastic, in fact, it was Steve Califf, who's the technical director of AMA, did a fantastic article that's on the AMA website, which is modelaviation.org, and he explains to the membership that when an individual shows up at your flying field with a DX6 or a spread spectrum system, it's just very similar to if they show up with a cell phone. It's the same type of technology. Those folks have been instructed to go ahead and allow you to fly. If you get to a flying event or you get to a flying field where folks aren't aware of spread spectrum technology, you can simply explain to them that it's spread spectrum. And if they insist on, they're unsure of the technology, which wouldn't be that uncommon, it would be a good idea to have the individual take their airplane and turn it on and to actually turn your system on, and you can very easily prove that it doesn't cause any interference. By wiggling the sticks, you can obviously see that they're not getting any interference, even when you're up close, far away. So, but the AMA is very active in promoting Spektrum technology, and they have also, if anybody has that question, forward them to the AMA website, which is, again, modelaviation.org, and it answers that question and tells their membership to just be confident, to go ahead and let the folks fly, and in fact, jump in and fly yourself with the same system. There's another really interesting aspect of the DX6. Park flyers and micro helicopters, because they're small, and per the namesake, you can fly them in parks. And the AMA is kind of having a little bit of an issue with that because there's a park or a backyard or a ball field that may just be right around the corner from a conventional flying field. So you have somebody at a flying field flying, maybe a high-dollar jet or a high-dollar aerobatic airplane, or even a 40 and 60 size trainer, and you have somebody right around the corner, within maybe a quarter of a mile, half a mile, or even within a mile, that's flying an airplane like this or a helicopter like you see here. And they're simply flying, and they're totally unaware that there's a flying field right around the corner, and vice versa. The guy at the flying field flying his $10,000 jet is totally unaware that somebody's flying a Yak or a Blade helicopter for the first time right around the corner. Well, the AMA thinks this is a great thing because now I won't interfere with the folks at the flying field. So it makes it a fantastic application for these park flyers because it eliminates the possibility of me interfering with those guys on 72 megahertz.
How critical is the receiver antenna installation?
As we discussed, the receiver actually has two antennas because there are two receivers built into the single receiver. In an ideal world, these two receivers would be mounted perpendicular to each other. In other words, one would be, maybe straight up and the other one at 90 degrees to the first one. That's in a perfect world. The reality is the margin of signal is so great. We talked about under poor conditions, you'll get maybe 12 to 1400 feet. At 1400 feet, you can't see this little airplane. So the reality of the situation is you have such a margin of range that the antenna installation is really non-critical. I have an ultimate here where the receiver is simply taped to the side of the fuselage and the antennas are simply just dangling. I mean, it would be more ideal if I taped these in place, but certainly this works fine. If I had a model aircraft that I needed to fly at the absolute as far as I possibly can at the absolute distance of my eyesight, I would be more critical about mounting these in the correct location. On this airplane, you know, if I get this thing more than 200 feet away, it's getting pretty darn small. And usually I fly this thing in my side yard and indoors. So consequently, like I say, the margins for range are just, it's not an issue. So typically, just install it, throw it in place. In the instructions, it explains, you know, kind of to set it up something like this and do a range check. If the range check's good, you're good to go.
Can I bind more than one receiver to the transmitter?
Yeah, that's a real common question that we get all the time. So the binding process is the process of teaching the specific receiver to listen only to this transmitter and absolutely nothing else. So there's over 4.2 billion possible combinations or codes in the transmitter, and I need to teach the receiver to listen only to the transmitter that I choose. And so that's done at the factory, but if I buy another receiver, of course, I need to teach it that code. And to do that, you simply plug in the bind button, power the system up, and the light will start blinking, and then on the transmitter, I push the bind button, turn on the transmitter, and again, the light starts blinking, and in about 10 seconds, the two start talking to each other. And I know that's a long answer for a short question, but the fact is I can do that with an infinite number of receivers. If I had 50 receivers sitting here in front of me, I could bind all of those to the same transmitter. And vice versa, if I then choose a different transmitter, I can bind any or all of those receivers to any transmitter that I choose. Binding process takes about 15 seconds, very simple to do.
If two transmitters somehow acquire the same channel, will I get shot down?
Yeah, people ask that quite frequently. And first off, according to the FCC, and there's a law of collision avoidance which states that when this transmitter's turned on, it has to scan the 2.4 gigahertz band and has to find an open channel. And then of course it does that a second time. So in theory, that can't happen. Now the only way that physically could happen is if you happen to be at a flying field that was over 3 miles away from where I'm at, and you turned on and your transmitter just happened to acquire the exact same 2 channels that my transmitter did, which is extremely unlikely. There are 80 possible channels. But let's say that happened. Then you get in your car and you drive to me with your transmitter on, and my transmitter remains on it the entire time. At some point, I would lose control of my model, but that point is only when your transmitter is 80% closer to the model than mine. So in other words, if you were 20 feet away from the model and I was 80 feet away from the model, at that point my model would go into failsafe. You would never be able to take over control, but certainly my model would go into failsafe at that point, and vice versa, your model would go into failsafe. So when the receiver sees the exact frequencies, 2 frequencies, and the signal strength is 80% greater than the controlling frequency, at that point the receiver goes into failsafe. The chances of that happening are extremely unlikely because of the 2 frequencies. The chances of your transmitter happens, and secondly, normally you don't travel when you do this. So on the ground, there is no time when both transmitters will be able to turn on the same frequency, and you'll be able to fly a model from my position close enough where it would cause interference to you. So that just can't happen. You know, anytime you're within about actually it's about 1.7 miles, the transmitters recognize each other. So they won't turn on the same frequency. And you can't fly a model that far away. It's impossible because you can't see it. So.
When will this technology be available for larger size aircraft?
Yeah, of course now this is for park flyers, which include micro helicopters and so on. And we explained that a part of that's range, but a good part of that is antenna fading. I can assure you we are working hard to bring this to the next level, the next size of aircraft. But there are a lot of technical difficulties in doing that. And unfortunately, there's no way I can answer that. There's actually some new technology that needs to be developed and is under development that we're working on that hasn't been developed yet. But we're trying and we're working on it. And gosh, I hope within a year or so. But it's really hard to say.
Okay. Hey John, can you go over setting the fail-safe positions and how they work one more time?
Sure. With the bind plug plugged into the bind receptacle, connect the battery or power up the receiver. In the case of an electric airplane, that simply means plugging in the battery. You'll notice if the bind plug is plugged in properly that the amber LED will flash, indicating that you're in bind mode. Now it's important to set the control sticks to the desired position, which is generally low stick, in fact almost always low stick, low throttle, and generally center the other sticks. This will preset your fail-safe position. Now, with the sticks set in the appropriate position, press the bind button and turn the transmitter on. And you'll notice that the bind button flashes for about 5 seconds, and then the system connects, and that's all there is to it.
How much are Spektrum receivers? Will they work with my current systems? And what do I need to do to convert my airplanes over?
Receivers sell for $60, $59.99. So that's the typical street price of a receiver. Now, of course, the only way to use a receiver, you have to use the Spektrum transmitter. So the Spektrum transmitter is not compatible with any other brand receiver, and this receiver is not compatible with any other brand. For example, I cannot use this with any existing JR, Futaba, Hi-Tech radio. These two must go together. The actual function of converting, for example, let's say I had a conventional JR radio in this particular airplane, and all I would need to do is open up this hatch, take out the receiver, and simply plug this in its place. The channels are clearly marked, and then of course I would need to bind it at a low throttle setting, and I would need to, of course, do the programming and adjustments, servo reversing, travel adjust, and so on. But it's very typical of installing any radio system. So it's very easy to do. $60 for the receiver. Receiver should be readily available.
The receiver looks awfully small. How much does it weigh?
It's actually 7 grams. So very small receiver. Of course, the receiver was designed specifically for these small ultralight airplanes. Another frequently asked question that we get is, does it have telemetry? And this system does not have telemetry. Our car systems that we introduced back in a year ago in January, actually we have telemetry available for that. But this was intended to be the lightest, smallest system possible, so hence we left out telemetry in this system. In future aircraft systems, we may incorporate telemetry if that's something that's desired. But in order to keep the smallest, lightest weight receiver possible for these type of aircraft, it's 7 grams, no telemetry.
Is the Spektrum system made by JR?
Actually, the transmitter and the hardware is manufactured by us, by the same people that make the JR radio systems. The technology and the boards and the electronics have been under development for nearly 7 years. Actually been under direct development for about the last 4 years. So this is a project that Horizon started a very long time ago. We developed the technology, and actually the boards and electronics were designed and developed and are being manufactured out in California. Those are being sent overseas to the manufacturer that makes the JR radios. And if you'll notice, this is actually an older JR radio called a 662. The 662 was utilized because it was a platform that allowed us to bring our technology to market pretty quickly. If we had to design and develop the hardware, basically the radio system, the case, and the gimbals from the ground up, unfortunately we wouldn't be here talking to you today about this radio system. We'd be busy, working on our computers, developing the system. So JR allowed us to use an existing transmitter and incorporate our electronics and our design into their hardware, and that allowed us to bring the product to market in a timely manner.